Okay, intrinsic coordinates. So these are pretty neat. So when do we use intrinsic coordinates? Well, we use them when we have something moving along a known path or trajectory. So like a roller coaster. So let's take a look at our roller coaster here. So we have this little guy and he's moving along this loop-de-loop track. Now this roller coaster, this little guy in his cart, he can't move anywhere other than on the track of the roller coaster, right? Our our cart is never gonna just like hop off the track and go this way. It is constrained. Its motion is constrained to the track. So at any point, its velocity is always tangent to the track, right? If he's here, the only direction our particle or our cart can move, it can either go this way, tangent to the track, or it can go this way, tangent to the track, right? If he's here, he can only go one of two ways. He can either go tangent to the track this way, or he can go tangent to the track this way, right? He can't go this way, he can't go that way, he can't go this way, he can't go anywhere other than the prescribed motion of the roller coaster track, right? He can only go that way, right? So his velocity can only be tangent to the track, right? Because he can only go that way or this way, whichever direction, tangent to the track. That's it. That's the only motion he can have, tangent to the track. So what we can do is we can attach this ET, EN, EB basis, which is our intrinsic basis, and we can attach this, and it moves with the track. So this basis moves with our particle along the track as our particle moves. So let's talk about the components of this basis. First, we have the ET, which is called the unit tangent vector. This is our unit tangent vector. It is tangent to the path / trajectory, and it is parallel to the velocity vector. So just like we were saying, our cart can only move in one of two directions. It can either move tangent to the track this way or tangent to the track that way. Let's just, for this example, just say that it's going to go in this direction, right? If we're at this point here, the only direction of velocity is this, right? It can only move in that direction. So that is the ET direction. ET is tangent to the track. It is parallel to the velocity vector, right? They both point in the same direction. They both point in the direction of the velocity, tangent to the track. Next, we have the EN vector, which is called the unit normal vector. It's perpendicular to ET, the unit tangent vector, and it points toward the center of curvature. So let's talk about this. Here's our EN vector. It is always going to be normal to our track. It's always normal to the track. See how this ET is pointing this way? It's tangent to the vector. EN is always normal to the track, and it's pointing in this direction. But there's another normal to the track, Brian. It could be normal to the track this way, right? Well, yeah, but it's not pointing, what'd we say, points toward the center of curvature. So it has to point in the direction that the track is curving, right? So you see how the track at this point, it's curving like that, it's curving like this. Well, then we want to point that way. I guess this will be the concave side. This will be the concave side. This way would be the convex side. This would be the concave, I guess. I'm not sure if that's the 100% correct terminology, but we point in the direction that we're curving. The direction we're curving. So we're curving this way, so we're going to point that way. So let's take another example. Say we're right here at the top of our roller coaster. Our E sub t vector is going to point like this. This will be E sub t. It's tangent to the track and pointing in the direction of the velocity, right? Because we're moving that way. That's our E sub t. And then our E sub n is going to point in this direction. Why that direction? Well, because at the top of this track, at this point here, our trajectory is curving like this. It's curving in this direction. And we're normal to the track, and we're going to point in the direction that we're curving. So it points in this direction, like that. I drew out a few other bases so we can see some examples. When we're going around this loop-de-loop, this circular loop-de-loop, we're going to point towards the center of curvature. The center of curvature would be right here at this, because it's just a constant circle. So our E sub n is going to be normal to the track and pointing in towards the center of curvature. And E sub t is going to point tangent to the track in the direction of the velocity, right? And then we did, this is my last one, E sub t points this way, E sub n is going to point straight down because the track is curving like this. Okay, I think we understand. So E sub b, this is our last direction, E sub b is called the unit binormal vector. The unit binormal vector. And it's just equal to E sub t crossed with E sub n. E sub t crossed with E sub n. So if we do E sub t crossed with E sub n, this is just going to point out of the page. Because this is a 2D example, E sub b is either going to be pointing into the page or out of the page. For this one right here, E sub t crossed with E sub n will result in E sub b being out of the page. Same here. E sub t crossed with E sub n is going to result in E sub b being out of the page. And I see an error I have here. Let me fix this. So E sub t crossed with E sub n at this point, E sub b is going to be into the page, right? So E sub b can either be pointing into the page or out of the page for a 2D example. That's it. That's the only choices it has. But that's how we define E sub b. It's just E sub t crossed with E sub n is E sub b. And this E, t, E, n, E, b basis, this is called our intrinsic basis. So now that we conceptually understand these directions of our intrinsic basis, let's actually put some math to it. So let's define these vectors. We know that the velocity of our particle is parallel to the tangent vector, right? I said that pretty exhaustively, I think. So we can just say our velocity vector is equal to the magnitude of the velocity in the E sub t direction, right? There's nothing wrong with that. That's how we can define the velocity that way. Our velocity vector is just equal to the magnitude of itself, and what direction is it pointing in? It's pointing in the tangent direction. Fine. Notice this little script v. This denotes speed. This is equal to the magnitude of the velocity vector. So we can say the magnitude of the velocity is equal to this number. It's a scalar speed in the E sub t direction. If we just divide out our speed, we'll end up with this right here, the definition for E sub t. And you can note that dividing by the speed, that makes it a unit vector. So this here is a unit vector. Notice the little hat above our E sub t. So this is our tangent vector definition. It's the velocity vector divided by speed. We know that E sub t and E sub n are perpendicular to each other. We did this in a previous video, and we're going to do it again here. So let's dot E sub t with itself. Well, a vector dotted with itself is 1. Okay, nothing wrong with that. That's a regular dot product rule. And now let's take the derivative of both sides. So d dt of the dot product of the vector with itself equals the derivative of the right side, derivative of 1. The derivative of the number 1 is the number 0, right? Derivative of a constant is 0. And then we're going to do the product rule between these guys. So derivative of the first times the second plus the first times the derivative of the second. This is going to be equal to 0. Remember, we can swap the order we do the dot product, and that allows us to add these together, right? So we have 2 of these. We have 2 det dt dotted with et, and that's equal to 0. We can divide out the 2, and then we end up with this right here. The derivative of et dotted with et is equal to 0. This tells us that its derivative and et are perpendicular because their dot product is 0, right? A vector dotted with itself is 1. A vector dotted with another vector that's perpendicular to it is 0, right? There's nothing to project onto that other vector. So let's just let that direction, let's let that perpendicular direction, we're going to call that en, but it's not a unit vector yet. So how do you make something a unit vector? Well, you divide it by its magnitude. So that's what we're going to do. Divide it by its magnitude. Now we made a unit vector. So this is our normal direction. Finally, E sub b, this is an easy one. It's just equal to E sub t crossed with E sub n. That's our unit binormal direction. And that's it. So we've now just defined all of our intrinsic directions. Intrinsic coordinates can live in 3D as well. I know the example I did up top with the roller coaster, that was a planar example, that was 2D, but nothing wrong with being in 3D. I use this all the time. Same principles apply. Say you have this Pringles chip, and you have a particle moving around the outer edge of our Pringle chip. E sub t is moving in this direction, tangent to the trajectory, right? The velocity is pointing in this direction at this point. E sub n is pointing towards the center of curvature, right? It's curving like this, right? So we're going to point in that direction, normal to the trajectory towards the center of curvature. And then E sub b is just E sub t crossed with E sub n gives you E sub b, right? And I drew a couple other bases here to show what it would look like if your point's here. Your velocity is pointing in this direction, parallel to E sub t. The chip is curving like this, chip is curving like that, and E sub n is normal to the trajectory and pointing towards the center of curvature. And then finally, E sub t crossed with E sub n is E sub b. Okay, and then the third one is just, there you go. You can think about that one on your own. So just some terminology. This is the last thing in the video. Some terminology you might come across. Curvature, that just means how fast the E sub t vector turns or curves. There's a term called torsion, and that's how quickly the trajectory twists, how quickly our basis is twisting. And then there's this term osculating plane, and that's just the plane formed by ET and EN. So it will be this plane right here. ET, EN, that's our osculating plane. On this one, it will be like this. That's our ET, EN. And that's it. There's mathematical meanings behind curvature and torsion, but I don't want to go into that in this video. I just want this to be a quick introduction. So that's it. That's our intrinsic coordinates. We'll do some examples in the next few videos, and I have some cool Python animations I made to kind of demonstrate and show an intrinsic basis moving along a trajectory to kind of visualize it. So I'll see you in those videos. Bye.